Hello and welcome to this session on the background or the basics that we need before starting off with the Fluent Solver. So we're going to learn what is the usual workflow in ANSYS Fluent, for which I expect that you're already familiar with the user interface and are familiar with the file structure of ANSYS Fluent, what are the different kinds of file formats, and the general idea about CFD terms and the numerics. So we're going to have a look at what is the usual workflow, how the different tasks are executed in ANSYS Fluent. We'll see the file handling options, certain options regarding how to set up the problem in terms of the model setups, the physical models, the boundary conditions, and the overall problem setup. And we'll also see how the CFD project also includes a solver setup. Now the solver setup includes usually things like the numerical schemes, how the finite volume method, which is at the background of ANSYS Fluent, which it is using to solve the given equations that are defined in the problem setup, how they have to be solved, what are the different numbers, different inputs which are necessary for things like under relaxation factors or Courant number. So this very much depends upon the solver. So we're going to have a look at them one by one. The overall execution of the tasks in ANSYS Fluent is basically defined in the outline tree, which you are familiar with from the user interface. So usually it includes, first of all, to import or scale or modify the mesh. First of all, we do this using the menu bar, and we can read in you can surely automate this whole process, but usually the process that we do usually is to first of all include the necessary physical models and the necessary material and properties of different materials included in our problem. We also have the operating and the boundary conditions defined, and once the overall problem is set up, we start initializing the problem. ANSYS Fluent 13 version onwards, we have some new features in initialization as well. We can set up the solver controls and start our iterative solver to compute a solution which we can monitor and analyze at the end. So this is how I will proceed with this lecture. So I'll be starting off with importing and scaling a mesh, which is part of the problem setup part. We'll be speaking about solver setup separately. So as far as importing and scaling a mesh is concerned, as you can see here, we read or write the necessary files using the menu bar on file options. Once we read in a mesh, we have different zones. Uh, Now this task is usually done at the pre-processing stage, that we have a collection of faces or collection of cells defined as zones or threads, which are understandable for the for ANSYS Fluent code, that it defines things as a collection of faces. It terms it as a face zone, or collection of cells. It defines it as a cell zone or a cell thread. So the zone and thread, this word I'll be using interchangeably, because thread is what the source code of ANSYS Fluent has, and also if you're writing user-defined functions. So basically, inlet is a group of inlet faces through which the flow comes in. The outlet zone is a collection of faces through which the flow goes out, or it may come in because of backflow conditions. Wall zones, and we can have fluid zones. So basically the zone or thread is helpful. This is a grouping which is done at the pre-processing stage. In ICEM CFD it's called part names. In Gambit it might be simply zone names, or in other packages they might have different classifications, but all that we are trying to do is to assign different zones which ANSYS Fluent understands. Now once we have a geometry like this is just an example of a server room cooling project we were involved in, and what you can see here is the different kinds of zones. So you have a collection of baffles which have been classified as one single zone called the baffle group. There are some different air handling unit inlets, so we have termed them a collection of faces as air handling unit 1 inlet, HU2 inlet, and so on and so forth. And we have a collection of grill wall faces. They have been also classified as grills, and there are some faces like bottom wall, inner wall, and outside wall, and there are some zones which we generated because of mesh convenience, mesh generation convenience, and they are termed as interior. Now it's a question whether we need to include interior zones or not. Actually, if we don't give any name and we export the mesh and read that mesh back into Fluent, Fluent considers um, all now this is actually a characteristic of your preprocessor. So if you're using Gambit and you're exporting a mesh, all the zones which have not been given names, let's say it's an external phase, then it will be termed as a wall. So we can include those names directly in the preprocessor like Gambit or ICEMCFD, but if we leave the names, we don't give any names, then in that case automatically some of the names, some of the zones are defined already at the pre-processing stage, and Fluent just reads that in. So these are the zones which were created, the part names that we created in the preprocessor, and Fluent retains those names. Let's say we forgot to mention some names. So in that case, if I'm using Gambit, then in that case all interior faces will be termed as interior, so the flow can pass through it. If I name them as walls, then in that case they will be treated as two-sided walls. But we also have other cases, external faces, which will be treated as walls. And if I don't assign any name to the um, so there are some zones, if we have not given them names, then in that case, if they are interior faces in Gambit, for example, they will be treated as interior zones. They will be automatically given an interior type of boundary. But if I'm using ICEM-CFD, it might happen that it will be given a wall type of boundary. External walls, external faces are anyway termed as wall in both ICM-CFD and Gambit. And if I don't give any name to the cell zone condition, cell zones in Gambit, then it is treated as fluid, but otherwise ICEM-CFD treats it as a wall or a fluid dependent upon the name. So these are some of the conventions which we use, and once we get the mesh into the solver, that is ANSYS Fluent, we have the names of the different zones accessible on the boundary conditions and the cell zone conditions panel. So if I click on any of them, you can see the different kinds of zones, and we can set up the specific properties of each zone. Let's say I click on tube inlet and I want to give the necessary velocity. So it is a velocity inlet type of zone. So the name was given in ICM-CFD or T-Grid or in Gambit, but the type is something which I can surely change in Fluent. I can even change the name. Actually, if I double click on it, I can change the name here in this zone name panel, and we can give specific inputs additionally. Now what is very interesting here is the zone ID. Now this is the ID with which the preprocessor saved the .msh file, and Fluent is accessing tube inlet not only by its name but also by its ID. And let's say I want to give a profile at the inlet, then in that case, and I want to give a, let's say, time varying profile at the inlet for velocity, and I want to use a user defined function for that case, then in that case what we can do in the user defined function is to access the thread ID 13, and we can give an appropriate boundary condition. So this is very helpful if I am using user defined functions to access such ID. All zones have an ID. These can be boundary condition zones or cell zone condition zones as well. So all of them have a specific thread ID or a zone ID which is unique in a given mesh file or a case file. Moving on to the geometry part and the mesh part, so we can also do a scaling as was already described in the previous lecture. So we can scale down or scale up a mesh. Fluent assumes that the mesh you have provided to it is in SI unit system, that is in meters. But let's say I created the mesh assuming that all dimensions were in mm, then we just need to apply the appropriate scaling. I can report to Fluent that please consider that I created the mesh was created in mm, and accordingly a factor of 10 to the power minus 3 will be scaled will be used for scaling the mesh. And what we can also see here is the domain extent, which is helpful to which can help us to gauge whether we are operating in the right dimensions. Let's move on to the physical model setup. Now Fluent has a variety of physical modeling capabilities. It has different kinds of physical models that you can include. So you can see here, you can activate whether the flow is multi-phase or single phase, if the energy equation is to be included or not included, if it's an isothermal flow that I want to simulate. I can also include radiation modeling effects or heat exchanger effects. Heat exchanger modeling can also be performed. I can include multiple species and multi-phase in the frame of Eulerian Lagrangian approach, and some other computational aeroacoustics simulation can also be done. So there's a huge variety of physical models that are available. Some of them have been listed down here. And what you can do is you can access them through the GUI as well as the text user interface. So some things are very visible on the GUI, as you can see in the previous slide. But if they are not accessible on the GUI, then you can also use some text user interface commands, type define on the terminal emulator, and you can see some hidden features, especially some turbulence models which are not available, like the mixing length model, are accessible through the TUI, although they don't show themselves up in the GUI. So there are a variety of physical modeling capabilities. This is how we can access them in ANSYS Fluent. Once we have defined the physical models, we move on to defining the materials. Now this will take some time to understand. The material types in Fluent are of primarily 5 types, but we would focus specifically on 2 types: fluid type and solid type. So there are different kinds of other kinds of materials, like mixture if it's a multi-species simulation, an inert particle, droplet particle, or combusting particle. These are all particles types, in case we are including an Eulerian Lagrangian kind of multi-phase model. But primarily what you will be usually dealing with is the solid and the fluid type of material. And the different kinds of properties that you need to give are usually dependent upon the physical models that you've included. If you have included it to be a single phase or a multi-phase problem, accordingly the inputs will be different. If I have included the energy effects to be taken into account, energy equation is going to be solved. In that case, there will be inputs for specific heat, thermal conductivity, and other heat transfer equation related inputs that will be required. And these properties can be either constant or a function of temperature. We'll be seeing this in a minute, how it can be done, especially for gases, because you can also have an ideal gas or a real gas equation which can be included. So you can see the material type. First of all, it's the mixture, fluid, or solid, and basically you can see the specific material. You can choose them here. Let's say we have a material, let's say another material which is similar to water. In that case, we can also include the properties of water and just change the name and click on this change create, and you will create a new material. Fluent also has a lot of materials in its own database, so we can also access the Fluent database appropriately. If I click on this Fluent database, then such a Fluent database materials panel opens up. We can access fluid or solid type, and we can select any of these materials whose properties can be copied. So once this is from the database, this is from the C drive or whatever is the directory in which you have installed Fluent, and from there, if I click on copy, this gets included into your case file. This is your current case file, and you're accessing from the database of Fluent into your case file. So now if you write a case file for your problem, it will also include the material, whatever you have chosen. Let's say I chose dichloromethane, CCl2. In that case, dichloromethane will also be available in the case file from now onwards if I write the case file in this case. And I can edit the properties once I'm here. The Fluent database values, I cannot edit it on this panel, but all the editing can be done in your existing case file. That is basically making some logic. In some cases, you can also define your own database, but that's a bit more for including more properties. But basically, Fluent database is quite extensive based on the NIST data available. Let's specifically look at the fluid material density. The fluid's density can be either a constant, it can be also chosen to be a incompressible variable density. When I say incompressible or compressible, usually the fluid's compressibility does not necessarily mean that the flow will also be compressible. The compressibility of a flow is defined whether the density of the fluid varies with the flow pressure. Unlike uh, a compressible fluid whose density is simply varying, and then you classify it to be a compressible fluid. But in the case of an incompressible or compressible flow, the determining quantity is whether the density is varying with respect to the flow pressure and not just let's say the temperature. So for example, you can have an incompressible ideal gas equation being solved in which the pressure remains constant. It's just the temperature which is inversely varying the density. So you can also include those effects. In such cases, the operating pressure on the operating conditions have to be specified. I'll speak about this in a minute. But you can also include an ideal gas equation or many real gas equation models which are available now in ANSYS Fluent. It can also be defined as a polynomial function. Let's say I have water. It does not qualify to be an ideal gas or a real gas. So we can also define its property variation in terms of density or other things with respect to a polynomial or a piecewise polynomial or a linear function of temperature. In case we are also including the compressibility effects of liquids, so liquids density is varying with respect to the pressure. Let's say there is an impact, there's a object falling into water, and we want to see how much elastic behavior the object experiences, the solid object experiences once it interacts with the liquid. In that case, we need to have a function for defining the compressibility factor of the liquid, and also the speed of sound needs to be defined. This work is usually done through a user-defined function. So you can see if I'm choosing for a gas like air, then you have a variety of choices for the compressibility effects to be included. We have many real gas models, especially from the release 13 for ANSYS Fluent, and there are the standard ideal gas and incompressible ideal gas, in which the density is only varying with respect to the temperature. So let's have a look at it more in detail, especially on the incompressible flows. So if you have a compressible flow, you can include the ideal or real gas law. But if it's an incompressible flow, you have a variety of choices, either to have a constant density or choose the incompressible ideal gas. This is very helpful, especially for natural convection kind of problems or mixed convection problems. You can also have convection or other kinds of phenomena which is influencing the density. So you can also have density varying as a function of temperature in a polynomial or piecewise linear, piecewise polynomial function of temperature. And this is again something which is valid for natural convection kind of problems. Otherwise, this does not really have a great significant effect on the flow phenomena. One very interesting model is called the Bosnisk model, which is again something which is very customized for natural convection problems. So this can be implemented if there are small changes in temperature which is causing a density variation along one direction primarily, that is along the direction of the gravity, because of which a natural convection phenomena takes place. So usually the Bosnisk model has a requirement that the thermal expansivity, this is thermal expansion factor, beta times the temperature difference between the ambient and the temperature of the object from which the natural convection phenomena is occurring, that this product should be much less than 1. In that case, the Bosnisk model is applicable. You can choose the Bosnisk model for the density variation. And in that case, the density variation along the gravity direction is approximated by a simple linear function of temperature. So you have density difference corresponding to a mean density times the thermal expansion factor times the temperature difference. Now this is quite useful if you want to do a simple natural convection problem, because natural convection problems usually have a lot of issues with convergence. So basically, once the material properties have been set, we have created or changed the properties of existing materials, then in that case we need to assign the fluid zone with that material. So we go to the cell zone conditions panel, we click on edit, and here is where we choose the material and we say okay, and then that material is the material included within this cell zone. So this is one part that you want to define the material in your existing case, but you want to assign that material to that specific domain that is to be done separately. So that is an additional step. Please don't miss it out, because often users commit this mistake that they forgot to include the material, they forgot to assign the material to the cell zone conditions. So let's move on to the operating conditions now. So we are going to have a look at what are the different ways in which the operating conditions need to be set up. The operating conditions include operating pressure. So this is basically the reference pressure that is defined for your problem. So all the pressure inputs in Fluent are actually with respect to this pressure. They are treated with respect to this pressure in gauge terms. I'll speak about why Fluent uses the gauge pressure values, but basically all these values can be also given in terms of either a constant value or a parameter, which are accessible from the workbench. Then so you can just click on this P icon here, and you can give that value, and which is then quantity which you can access from the ANSYS workbench. And the other thing that you need to assign is the reference pressure location. So it should be that point in which the pressure is not varying drastically during the flow. And it's useful for incompressible flows if I am using the outflow boundary condition and I don't know the pressure, I just know the mass flow inlet and I want to assign the outflow boundary condition. I'll speak about these boundary conditions in the lecture on boundary conditions, which is going to follow up to the solver basics lecture. And in such cases it's very helpful to determine what is the pressure, what is the flow pressure at the exit for this given mass flow rate. Or let's say I give that as a specific location. In that case, all the pressures will be evaluated with respect to that pressure location. In addition to this, if I want to include body force terms in terms of gravity or some other effects, I can specify the x, y, and z coordinates of the gravitational acceleration direction. Let's say I have an electric field. In that case, I can also include additional um, acceleration term, so meter per second square term. I can also change its units if I want. I can I can have additional value, not just this typical 9.81 if my flow, if my mesh is arranged in this way that the gravity is acting downwards in the negative y direction, but you can also assign it as your geometry or your mesh is aligned along the coordinate axis. And these some additional parameters like specified operating density or operating temperature. I will be discussing this in the subsequent slides.